Okay, I'm going through the fluids project. I'm going to start with analytical, move on to finite differencing, and then COMSOL. For the analytical, you can start with the continuity equation, and you can move that by simplifying down to the x-directed momentum balance. You can simplify that down, and by applying boundary conditions, I had y equals 0 or v of x equals the velocity of the belt. And for boundary condition 2, I have y equals h equals v of x equals 0. You can integrate the equation that you had from this momentum balance twice. You can apply boundary conditions to get this final equation. You can also solve for a numerical value of that. I will show you how to get that later. Reynolds value, you can take this value and you can solve for to get 21.3, which confirms that it is in fact laminar flow. For finite differencing, that's COMSOL. Finite differencing, this is where I have finite differencing. I use solver for part of it, but the finite differencing is the blue dots, and analytical is graphed in orange lines. And volumetric flow. Actually, before I move on to that, the difference between analytical solutions and finite differencing is that analytical solutions, you have one general equation that you can use to solve anywhere in the profile that you're looking at. The downside to that is you need to have a relatively simple profile you're looking at. If it gets too complicated, then it doesn't work anymore. Finite differencing, you can have more complicated profiles because you're just looking at point values down the profile you're looking at. It's not an overall equation. The problem with that is that it's more of an estimate as compared to analytical solutions being more exact. But I solved for the volumetric flow and everything else past that with the analytical solution. So to solve for volumetric flow, you want to integrate over the velocity from 0 to h and multiply that by w, and that ends up getting you 0.0424 meters cubed per second. You can solve for the max velocities and how that would show up in the velocity profile. The point where it is the max is 2 times the pressure gradient divided by 2 mu times w plus c1, that's giving you 1.8 centimeters. And you can plug that value into the velocity profile, that's getting you 123 centimeters per second or 1.23 meters per second. The average velocity that I showed earlier is just integrating 0 to h times over the velocity, and that's multiplied 1 over h, or that is just q over w times h, and I'm going to use 0.883 meters per second. You can solve for the shear forces on the stationary wall and the moving belt or the moving wall. For the moving wall, you're taking mu times c1 to get tau, then and you 3.89 times 10 to the second pascals. You can multiply that value by the area, which is W times L, and that ends up getting you 14,000 newtons. And for the wall that is stationary, you can solve for tau by taking mu times 2 times the pressure gradient over 2 mu times h plus c1. You can take that value times the area again, which is the same as was before, W times L. And that ends up getting you negative 1,710 newtons. It's negative because the direction of the fluid flow in the way that we defined, I guess I defined, I was one of this day, but the way that I defined like my x coordinates. So it it's negative for a reason. These are the graphs, and I have some screenshots, but I can just show you what I did in the Excel. But this is, once again, the Excel document. That's the graph I have for the finite differencing and analytical solutions. This is the COMSOL one that I have. I just exported the data from COMSOL itself. I made a graph in Excel. But to show you COMSOL, I have the exact same graph in COMSOL. So I also have the velocity profiles. You can see that for the moving wall versus the stationary wall, you can see that it's kind of like an off-shape parabola. And then I also have the pressures. And I use the line averaging from the line integration to solve for the shear force, and this is the moving wall, right? Yes, that is correct. Yes, you are the moving wall. Yay. Okay. And then on average two. Probably should rename that, but whatever. This one is the stationary wall. And to explain things I had struggled with, I didn't realize that you could just multiply directly in this expression thing. Spent forever trying to see what magical buttons I should be pressing, and in reality, it was just multiplication time. Yay, me. Okay, well, thank you. Have a great break.